There is a moment, recorded in the flight logs of the United States Air Force in the 1960s, when a single American bomber flew from New York to Paris in 3 hours, 19 minutes, and 41 seconds. Not a fighter jet, not an experimental rocket plane. A bomber, a nuclear-armed strategic bomber, built to penetrate Soviet air defenses at twice the speed of sound, carrying enough destructive power to erase a city from the map. That flight, that extraordinary, almost casual demonstration of speed that would have seemed like science fiction to the pilots who flew propeller-driven aircraft just 15 years earlier, was made by the Convair B-58 Hustler. And it was, in many ways, the least surprising thing this aircraft ever did. Because the B-58 Hustler was not simply a fast airplane. It was a revolution in aviation technology, a machine so far ahead of its time that the Air Force that operated it never entirely figured out how to use it properly, and a weapons system so complex, so demanding, and so unforgiving of human error that it killed its crews at a rate that shocked even the hard-edged professionals of Strategic Air Command. It was beautiful. It was brilliant. It was dangerous beyond almost any aircraft in American military history. And today, we are going to tell its complete story. Let us begin where all great stories of technological ambition begin, with a problem that seemed impossible to solve. By the late 1940s, American military planners were confronting a reality that was reshaping everything they thought they knew about strategic bombing. The Soviet Union was developing jet-powered interceptor aircraft of rapidly improving capability. The MiG-15, which had shocked American pilots over Korea with its speed and climbing ability, was only the beginning. Soviet air defense networks were growing denser, more sophisticated, and more lethal by the month. Radar coverage was expanding. Anti-aircraft artillery was improving. And the high-altitude sanctuary that had protected the B-36 Peacemaker from interception, that precious window of relative invulnerability above 40,000 feet, was closing faster than anyone had anticipated. The question that American aviation engineers and Air Force strategists found themselves wrestling with in the early 1950s was one that would define military aviation for the next 2 decades. If you cannot fly high enough to be safe, can you fly fast enough? Speed, as a defensive strategy, had a logic that was both compelling and ancient. A target that moves fast enough is simply harder to hit. An interceptor that cannot catch a bomber cannot shoot it down. A surface-to-air missile that cannot keep up with its target cannot destroy it. If a bomber could fly fast enough that the entire Soviet air defense system, from its radar operators to its interceptor pilots to its missile batteries, could not react quickly enough to engage it effectively, then speed itself became armor. Speed became survival. Speed became the difference between a successful nuclear strike and a crew that never came home. The threshold that American engineers identified as the practical minimum for this speed-as-survival strategy was Mach 2, twice the speed of sound, approximately 1,500 miles per hour at altitude. No operational aircraft had ever flown at Mach 2. It had barely been proven theoretically possible for anything larger than an experimental rocket plane. And the United States Air Force wanted a bomber that could do it routinely, carrying nuclear weapons across intercontinental distances. Convair, the same company, now under a different corporate name, that had built the B-36, responded to this requirement with a design that was, by any measure, one of the most audacious in the history of aviation. The B-58 Hustler was a delta-wing aircraft, a configuration chosen specifically because the triangular planform of a delta wing provides the structural efficiency and aerodynamic characteristics needed for sustained supersonic flight in a way that conventional swept-wing designs cannot match. The delta wing was not new. German engineers had explored it during the Second World War, and several experimental aircraft had used it, but no one had ever built a large, operationally capable combat aircraft around it. The B-58 would be the first, and for years, the only one. But the wing was only the beginning of the B-58's radical departures from conventional design. The aircraft's propulsion system consisted of 4 General Electric J-79 turbojet engines, the same engine that powered the F-104 Starfighter and would later power the F-4 Phantom, mounted in individual pods beneath the wing rather than in the wing or fuselage. This pod-mounted arrangement allowed each engine to be removed and serviced independently, a maintenance advantage that proved significant in practice. The J-79 was itself a remarkable piece of engineering, a variable stator turbojet capable of producing approximately 15,800 pounds of thrust with afterburner, and featuring an innovative compressor design that made it efficient across a wide range of airspeeds. 4 of them, burning afterburner, could push the B-58 to speeds that made everything else in the American military inventory look stationary. The fuselage of the B-58 was long, slender, and extraordinarily carefully shaped, every curve and contour calculated to minimize aerodynamic drag at supersonic speeds. The aircraft's cross-section followed the area rule, a principle discovered by NACA researcher Richard Whitcomb in the early 1950s, which showed that the total cross-sectional area of an aircraft must change gradually along its length to minimize the wave drag that limits supersonic performance. The B-58's fuselage was noticeably wasted, pinched in at the middle in a way that was immediately visually distinctive, as a result of applying the area rule to its design. This waste became one of the aircraft's most recognizable visual features, giving it a sensuous, almost organic quality that was in striking contrast to the angular, functional appearance of most military aircraft. The crew of the B-58 consisted of 3 men: pilot, navigator bombardier, and defensive systems operator, seated in tandem in individual cockpits, each separated from the others by sections of fuselage. This arrangement was chosen for aerodynamic reasons. A wide cockpit that accommodated crew members side by side would have created unacceptable drag at supersonic speeds. But it had profound operational implications. The 3 crew members of a B-58 could not communicate face-to-face, could not pass documents or equipment between stations, could not help each other with physical tasks during flight. They were connected by intercom and by shared purpose, but physically isolated in their individual cockpits in a way that was unusual even in an era when most bomber crews were accustomed to living in close quarters for long missions. And then there was the feature that gave this video its subtitle. The feature that, when it was revealed to the public and to the aviation world, produced a combination of admiration and genuine alarm that has rarely been equaled in the history of weapons development. The B-58's crew escape system. In conventional aircraft of the period, crew escape in an emergency was accomplished by the crew members opening their canopies and physically bailing out, jumping or being thrown from the aircraft, deploying a parachute, and descending to Earth. This system worked reasonably well at the speeds and altitudes at which most aircraft operated. At Mach 2, it was simply not survivable. A human body ejected at 1,500 miles per hour would be subjected to aerodynamic forces of such magnitude that survival was essentially impossible. The wind blast alone, hitting a human face and body at supersonic speed, would be instantly fatal. And even if a crew member somehow survived the initial blast, the deceleration from Mach 2 to parachute speed would subject the body to G-forces that no human physiology could withstand. The solution that Convair's engineers developed for this problem was, depending on your perspective, either a stroke of genius or a monument to the extraordinary lengths to which engineers will go to solve a problem that perhaps should have caused them to reconsider the entire premise. Each of the 3 crew members of the B-58 sat in an individual escape capsule, a clamshell enclosure that, when activated, closed around the crew member completely, sealing them inside a protective cocoon of metal and foam. The capsule was then ejected from the aircraft by a rocket charge, carrying the crew members safely through the supersonic slipstream inside their protective shell. Once clear of the aircraft and slowed to survivable speeds, the capsule deployed a parachute and descended to Earth. At the point of landing, whether on water or on land, the capsule served as a flotation device or a survival shelter containing emergency supplies, a radio beacon, and other survival equipment. The concept was extraordinary. The execution required solving engineering problems that had never been solved before. The capsule had to be strong enough to protect its occupant from the forces of ejection at Mach 2. It had to seal quickly enough that the crew member inside would not be exposed to the lethal wind blast even for fractions of a second. It had to be light enough to be carried by an already heavily loaded aircraft. It had to be reliable enough that crew members would trust their lives to it. And it had to be designed so that it could be operated by a crew member who might be injured, disoriented, or operating under enormous psychological stress in a combat emergency. The Stanley Aviation Corporation, which developed the capsule system under contract, spent years and enormous resources solving these problems. The result was a genuine engineering achievement, one of the most sophisticated crew escape systems ever created, and one of the most expensive components of an already enormously expensive aircraft. Testing of the capsule system produced results that were both reassuring and sobering. High-speed ejection tests using instrumented dummies showed that the capsule could protect its occupant from the aerodynamic forces of ejection at Mach 2. But real-world use during accidents and emergencies showed that the system, however well designed, was not infallible. There were cases where capsules functioned perfectly and crew members survived emergencies that should by any conventional analysis have been fatal. And there were cases where capsules failed, where the sealing mechanism did not operate properly, where the rocket charge malfunctioned, where the parachute did not deploy, with results that were terrible. The B-58's escape capsule was a brilliant solution to a genuine problem, and it saved lives that would otherwise have been lost. It also, on occasion, failed in ways that cost lives. Like almost everything about the B-58, it was simultaneously impressive and tragic. The B-58's weapon system was as unconventional as its escape system. Where most bombers of the period carried their weapons internally, in bomb bays, the B-58 carried its primary nuclear weapon in a large pod attached to the underside of the fuselage. A pod that was not simply a bomb carrier, but an integral part of the aircraft's aerodynamic and fuel system. The MB-1C pod, which was the primary weapons configuration for most of the B-58's operational life, contained both a nuclear weapon and additional fuel, the extra fuel occupying the forward section of the pod, the weapon in the rear. This arrangement was chosen partly for aerodynamic reasons. Having the weapon external but conformally shaped to the fuselage allowed it to be carried with less drag than a conventional external store, and partly because the B-58's slim fuselage simply did not have space for a conventional internal bomb bay large enough to carry the nuclear weapons of the period. The pod was released over the target, both the fuel component and the weapons separating from the aircraft simultaneously, and the aircraft then turned away and accelerated to escape the blast radius of the detonating weapon. This escape maneuver was itself a critical element of B-58 tactics. A nuclear weapon detonating beneath an aircraft that has not placed sufficient distance between itself and the blast is as lethal to the delivering aircraft as to the target. B-58 tactics specified a particular escape maneuver, a rapid climbing turn at maximum power that placed the aircraft as far as possible from the detonation point in the shortest possible time. Calculating the parameters of this maneuver, the correct airspeed, the correct bank angle, the correct timing of the weapon release, was one of the navigator bombardier's most critical responsibilities. The navigator bombardier's station in the B-58 was, for its era, a marvel of avionics sophistication. The aircraft's navigation and bombing system, designated the Sperry and /ASQ 42, integrated inputs from multiple sources: inertial navigation, Doppler radar, stellar navigation, and astro tracker, to provide continuous position information of extraordinary accuracy. The bombardier component allowed automatic weapon release calculated to deliver the weapon within the specified circular error probable, the measure of bombing accuracy used by military planners, even at Mach 2 bombing speeds where manual calculations would have been impossible. The system was so complex that navigator bombardiers underwent training lasting many months before they were considered qualified to operate it in combat. And even then, it was demanding enough that crew members who had flown the B-58 for years continued to find new subtleties and complexities in the system's operation. The defensive systems operator, the third crew member, occupying the rearmost cockpit, was responsible for managing the B-58's electronic warfare systems and its defensive armament. The aircraft carried a single General Electric T-171 rotary cannon and a tail mounting, a weapon capable of firing enormous volumes of 20mm ammunition in a very short time, intended to engage pursuing Soviet interceptors. But more important than the gun were the electronic warfare systems, the radar warning receivers, the jamming equipment, the chaff and flare dispensers, that were the B-58's primary defensive tools in the electronic warfare environment of the Soviet air defense system. The defensive systems operator's job was to monitor the electronic environment around the aircraft continuously, identify threats, and deploy countermeasures at the correct moment to defeat Soviet radars and missile guidance systems. It was highly technical, highly demanding work that required both deep knowledge of Soviet electronics and the ability to make rapid, high-stakes decisions under pressure. The first flight of the XB-58 prototype took place on November 11, 1956, at Carswell Air Force Base in Fort Worth, Texas, the same base where the B-36 had made its first flight a decade earlier. The test pilot was Beryl Erickson, the same Beryl Erickson who had flown the B-30 SIX's first flight, a continuity that speaks to the extraordinary career of one of America's greatest test pilots. Erickson found the B-58 an entirely different experience from the B-36, where the Peacemaker had been vast and majestic and slow to respond. The Hustler was taut and precise and demanding, a machine that rewarded skillful handling instantly and penalized mistakes with equal immediacy. It accelerated with a violence that was startling even to experienced jet pilots. It climbed at rates that seemed implausible for an aircraft of its size. And at Mach 2, it was like nothing any pilot had ever flown before, a machine operating at the absolute edge of what was aerodynamically and structurally possible, vibrating with the energy of its 4 afterburning engines, surrounded by the shock waves and heating effects of sustained supersonic flight. The development program that followed the first flight was long, expensive, and extraordinarily challenging. Flying at Mach 2 created engineering problems that the industry had only partially solved in the laboratory, and that became fully apparent only when actual aircraft were flown in the actual operational environment. Aerodynamic heating, the rise in skin temperature caused by friction with the air at supersonic speeds, required the use of special materials and construction techniques throughout the aircraft. The leading edges of the wing and the nose of the aircraft reached temperatures that would have damaged conventional aluminum alloys. Special high-temperature alloys and honeycomb sandwich construction techniques were developed specifically for the B-58 program. Fuel management at supersonic speeds created challenges that required elaborate automated systems to handle. The complex avionics of the navigation and bombing system required extraordinary quality control in manufacture and extraordinary care and maintenance to keep them functional. The B-58 formally entered operational service with Strategic Air Command in 1960, equipping initially the 43rd Bombardment Wing at Carswell Air Force Base, and subsequently the 305th Bombardment Wing at Bunker Hill Air Force Base in Indiana. The two wings together eventually operated approximately 80 B-58s, a relatively small number compared to the hundreds of B-47s and B-52s that formed the bulk of SAC's fleet, and a reflection of both the B-58's high cost and the Air Force's continuing uncertainty about how best to use it. Curtis LeMay, by now Air Force Chief of Staff after his long tenure commanding SAC, was not the B-58's greatest enthusiast. LeMay was a pragmatist above all else, and from a pragmatic standpoint the B-58 had significant limitations that offset its spectacular performance. Its range, even with the fuel carried in the weapons pod, was substantially less than that of the B-52. It could not be refueled in flight as easily as larger, more stable aircraft. Its maintenance demands were extraordinary. Keeping a B-58 mission-ready required far more maintenance hours per flight hour than any other aircraft in SAC's inventory. And its crew of 3, compared to the B-52's crew of 6, meant that it was less capable of sustaining long missions in the demanding, fatigue-inducing conditions of nuclear alert operations. These limitations were acknowledged by B-58 advocates, who argued that they were more than offset by the aircraft's speed, that a Mach 2 bomber that could penetrate Soviet air defenses successfully was worth 10 subsonic bombers that could not. This argument had genuine merit, and it reflected the core logic of the B-58's design. The problem was that the Soviet air defense system was evolving faster than anyone had anticipated. By the early 1960s, when the B-58 was just entering operational service, the Soviet Union had deployed surface-to-air missiles, the SA-2 guideline system, the same weapon that shot down Francis Gary Powers' U-2 reconnaissance aircraft in May of 1960, in significant numbers around its high-value targets. The SA-2 was capable of engaging targets at speeds and altitudes that made even the B-58 vulnerable. Mach 2 at high altitude, it turned out, was not immune to sophisticated surface-to-air missiles. The window of speed survival was closing just as it had opened. The Air Force's response to this development, and it was a response that had enormous implications not just for the B-58, but for the entire philosophy of strategic bombing, was to abandon high-altitude penetration and move to low-level attack tactics. Instead of approaching targets at high altitude and high speed, bombers would now fly at very low altitude, 50 to 200 feet above the terrain, in some cases, where terrain masking would prevent radar detection until the aircraft was very close to its target, and where the low altitude and high speed combined to make it extremely difficult for surface-to-air missiles to engage them effectively. Low-level flight at high speed is an extraordinarily demanding form of flying, requiring continuous attention and precise control. And the B-58, designed and optimized for high-altitude Mach 2 flight, was not ideally suited to it. Flying the B-58 at low level revealed aerodynamic and structural characteristics that were manageable at altitude but problematic close to the ground. The delta wing, so efficient at supersonic speeds and high altitudes, was less well suited to the turbulent air encountered at low level. The aircraft was harder to control in gusts and turbulence than conventional designs. The ride quality, the degree of buffeting and vibration experienced by the crew, was severe enough at low level to be physically exhausting during extended missions. And the engines, optimized for performance at altitude, were less efficient at the dense air of low-level flight, reducing the aircraft's already limited range. The B-58 was being asked to perform a mission for which it had not been designed, in conditions for which it was not optimized, and the results were predictably difficult. It was in this period of operational transition, with the B-58 being pushed toward low-level missions it was poorly suited for, that the aircraft's accident rate reached levels that caused deep concern throughout the Air Force. The B-58 had always been a demanding aircraft to fly. It required more skill, more attention, and more precise control than any other aircraft in SAC's inventory, and the consequences of errors were swift and severe. But the combination of low-level operations, the complexity of the avionics system, and the inherent characteristics of the delta wing in turbulent air produced an accident rate that was, by the standards of even the demanding world of 1960s military aviation, genuinely alarming. Between 1960 and 1970, the B-58 suffered 26 major accidents, resulting in the loss of 22 aircraft and the deaths of 36 crew members. This represented a loss rate, measured as the number of aircraft lost per 100,000 flight hours. That was substantially higher than any other aircraft in SAC's fleet. To put it in human terms, of the approximately 500 aircrew members who flew the B-58 during its operational life, roughly 7% died in non-combat accidents. For every 100 men who strapped into a B-58 and flew it operationally, 7 did not come home. This was not war. This was peacetime flying. And while military aviation has always accepted higher risk than civilian aviation, even by the standards of the era and the mission, the B-58's accident rate was extraordinary. The accidents took many forms. Some were the result of mechanical failures, engine problems, systems malfunctions, structural issues that the demanding conditions of supersonic flight gradually revealed. Some were the result of the aircraft's unforgiving handling characteristics in certain flight regimes. A B-58 that departed from controlled flight at low altitude gave its crew essentially no margin to recover. Some were the result of the demanding avionics system malfunctioning at critical moments. And some were the result of the simple, terrible reality that flying a Mach 2 bomber at low level, in all weather, day and night, over terrain that left essentially no margin for error, was one of the most demanding things that human beings had ever been asked to do in a flying machine, and that even extraordinary pilots sometimes made mistakes or encountered situations that the B-58 would not forgive. The escape capsule, in many of these accidents, was the difference between death and survival. Crew members who activated their capsule systems in time and whose capsules functioned correctly survived incidents that should have been unsurvivable. Aircraft that disintegrated in flight, aircraft that struck the ground at high speed, aircraft that experienced catastrophic structural failures. The capsule's ability to protect its occupant from the aerodynamic blast of supersonic ejection and to serve as a survival shelter after landing saved lives that would otherwise certainly have been lost. But in accidents that occurred at very low altitude, or that were too sudden to allow crew members to activate the capsule in time, the system's limitations were tragically apparent. An aircraft that strikes the ground at Mach 0.9 at 50 feet altitude gives its crew approximately 0.03 seconds from the moment of impact to the moment when survival becomes impossible. No escape system designed by human engineers can address that reality. The B-58 nonetheless accumulated a remarkable record of performance in the assessments and competitions that Strategic Air Command used to evaluate its combat capability. In the annual bomb navigation competitions, SAC's version of the Military Olympics, in which crews competed to demonstrate the accuracy of their bombing and navigation over realistic simulated combat profiles. B-58 crews consistently performed at or near the top. The combination of the ASQ 42 navigation and bombing systems accuracy, the aircraft's speed, which compressed the time available for errors to accumulate in a bombing run, and the exceptional skill of the crews that B-58 wings attracted produced bombing accuracies that impressed even the most skeptical SAC evaluators. In terms of delivering a nuclear weapon within the required circular error probable from a Mach 2 approach, the B-58 was genuinely formidable. The aircraft's speed record achievements, meanwhile, attracted public attention that the classified details of its combat capability could not. In January of 1961, a B-58 flew from New York to Los Angeles in 2 hours, 58 minutes, and 52 seconds, less than 3 hours to cross the continental United States. In May of 1961, a B-58 flew the 3,345-mile distance from New York to Paris in 3 hours, 19 minutes, and 41 seconds, the flight mentioned at the opening of this script, averaging over 1,000 miles per hour for the entire crossing. The crew, led by Major William Payne, received a hero's welcome in Paris and the Mach Trophy for the most meritorious flight of the year. In 1963, a B-58 flew from Tokyo to London, a distance of approximately 8,000 miles, in 8 hours, 35 minutes, and 20 seconds, with multiple aerial refueling stops. These were not simply record-breaking flights for the sake of publicity. They were demonstrations, carefully planned and executed by Strategic Air Command, of the B-58's ability to project American air power over intercontinental distances at supersonic speed, demonstrations intended as much for Soviet intelligence analysts as for the American public. The B-58 also participated in a series of nuclear weapons tests during its operational life, contributing to the American program of weapons development and validation that continued through the early 1960s. The specific details of these tests remain largely classified, but the general outline is known. B-58s delivered test weapons at proving grounds in the Pacific and Nevada, validating both the weapon's performance and the aircraft's delivery accuracy under realistic conditions. These missions, flown by crews who were not told the full yield of the weapons they were delivering and who wore dosimetry badges to measure radiation exposure, were among the most demanding and least publicized of the B-58's operational career. The Cuban Missile Crisis of October 1962 brought the B-58 to the highest state of alert in its operational history. When President Kennedy announced on October 22, 1962, that American reconnaissance aircraft had discovered Soviet ballistic missiles in Cuba, Strategic Air Command placed its entire nuclear force, including all operational B-58s, on DEFCON 2, the second highest alert status, one step below actual war. B-58 sat on the alert ramps at Carswell and Bunker Hill, armed with nuclear weapons, crews in their cockpits, or in the alert facilities adjacent to the ramps, engines ready to start, waiting for the order that would send them against Soviet and Cuban targets. For 13 days, those crews waited. Some of them have said in later interviews that they genuinely believed they were going to war, that the order was coming, that they would be flying combat missions against targets that would mean the end of civilization as they knew it. The order never came. Khrushchev agreed to remove the missiles. The alert was stood down. The crews climbed out of their cockpits, drove back to their quarters, and tried to sleep. What is not widely known outside of military history circles is how close the Cuban Missile Crisis actually came to producing exactly the exchange that the B-58 and its companion aircraft were designed to execute. The records that have been declassified in the decades since reveal a crisis that was far more dangerous than it appeared even at the time. One in which miscommunication, mechanical malfunction, and human error at multiple points could easily have triggered the very war that everyone was trying so desperately to prevent. In this context, the B-58s sitting on the alert ramp at Carswell were not abstract weapons of deterrence. They were loaded guns held by nervous men, aimed at a nervous adversary who had his own loaded guns aimed back. The piece that survived the Cuban Missile Crisis survived by a narrower margin than most people will ever know. The B-58's operational career was, in the end, shorter than anyone had anticipated when the aircraft entered service. The same combination of high operating costs, demanding maintenance requirements, limited range compared to the B-52, and the shift away from high altitude to low-level tactics that had plagued the aircraft throughout its service life continued to accumulate arguments against its retention. By the mid-1960s, The Vietnam War was consuming enormous resources and focusing American military attention on conventional, rather than nuclear, warfare, and the B-58, with its specialized nuclear mission and its lack of any conventional bombing capability, was irrelevant to that conflict. The McNamara Defense Department, with its emphasis on systems analysis and cost-effectiveness, looked at the B-58's maintenance costs, its accident rate, its limited range, and its narrowly specialized mission, and found it difficult to justify. The decision to retire the B-58 was made in 1969, and the aircraft began leaving active service that year. The last B-58 was retired from Strategic Air Command on January 31, 1970, less than 10 years after the aircraft had entered operational service. For an aircraft that had cost over $3 billion to develop and produce, and that had represented the absolute cutting edge of American aerospace technology, the retirement was abrupt and the career was brief. 86 B-58s were ultimately flown directly from their operational bases to Davis-Monthan Air Force Base in Arizona, the Air Force's aircraft storage and disposal facility, where they were preserved briefly before being cut up and smelted. Others were used as ground training aids, stripped of usable components and left to deteriorate. Of the 116 production B-58s built, only 8 complete aircraft survive today. Those 8 survivors are scattered across the United States at air museums and memorials, and they continue to draw visitors who come specifically to stand in the presence of this remarkable aircraft. The B-58 is, even today, a visually arresting machine. The delta wing, sweeping back from the needle-sharp nose at a 60-degree angle, gives the aircraft a quality of pure aerodynamic efficiency that is immediately apparent to anyone who understands aircraft design. The 4 engine pods, hanging beneath the wing in their individual nacelles, suggest barely restrained power. The slender fuselage, wasted in the middle in conformance with the area rule, has a sculptural elegance that most military aircraft of any era lack. And the individual crew capsules, visible as separate bubbles behind their individual transparencies, hint at the extraordinary technology packed into every corner of this machine. The aircraft on display at the National Museum of the United States Air Force at Wright-Patterson Air Force Base is the most accessible of the survivors, and it rewards careful examination. Standing beneath the wing, looking up at the pod mounting points, examining the escape capsule transparencies and the complex geometry of the Delta planform, it is possible to sense something of what it must have been like to fly this aircraft. The combination of extraordinary capability and extraordinary demand, the sense of operating at the absolute frontier of what was technologically possible. The B-58 asked more of its crews than almost any aircraft in history, and its crews responded with a level of professionalism and dedication that deserves to be remembered. The legacy of the B-58 Hustler extends well beyond its relatively brief operational service. The technologies developed for the B-58 program, the area rule, fuselage shaping, the pod-mounted engine arrangement, the advanced avionics integration, the high-temperature structural materials, the escape capsule system, influenced the design of virtually every American supersonic aircraft that followed it. The F-111, the State Route 71, the F-15 and F-16, even the later B-1 Lancer, all carry technical DNA from the B-58 program. The problems that B-58 engineers solved: how to build a large aircraft that can sustain Mach 2 flight reliably, how to navigate accurately at supersonic speed, how to deliver weapons with precision from a platform moving at 1,500 miles per hour, were problems that every subsequent supersonic military aircraft had to solve, and the B-58 program provided a foundation of knowledge and experience that made solving them faster and cheaper for the aircraft that followed. The B-58 also changed how the Air Force thought about crew training and crew selection. The aircraft's demanding handling characteristics and unforgiving response to errors led SAC to implement more rigorous pilot selection processes for the B-58 wings, processes that emphasized not just flying skill, but the specific cognitive and personality characteristics associated with performance under the sustained stress of high workload, high-consequence aviation. The detailed study of what made a successful B-58 crew member contributed to a broader understanding of human performance in high-demand aviation environments that influenced training and selection practices throughout the Air Force, and, eventually, throughout civil aviation as well. The men who flew the B-58, the pilots, navigator bombardiers, and defensive systems operators of the 43rd and 305th Bombardment Wings, form one of the most select communities in the history of American military aviation. The combination of the aircraft's demanding selection process, its challenging operational environment, and the tight-knit nature of the B-58 community produced bonds among crew members that have persisted for decades. Veterans of the B-58 wings have maintained contact through organizations and reunions, sharing memories of an aircraft and a time that were, by any measure, extraordinary. Their accounts of flying the Hustler capture both its brilliance and its dangers with a candor and specificity that official records cannot match. The visceral experience of afterburner takeoffs that pushed you back in your seat with a force like a punch. The surreal calm of cruising at Mach 2 above 60,000 feet, where the sky was dark enough to see stars in daylight. The focused concentration of a bombing run where a half-second's inattention could mean the difference between a hit and a miss that would be analyzed and discussed for weeks in the debrief room. There is one story, told by a veteran B-58 navigator bombardier, that captures something essential about the aircraft and the men who flew it. He describes a training mission in the mid-1960s, flying a simulated low-level nuclear strike against a defended target somewhere in the American Southwest. The aircraft was at 500 feet, at Mach 0.9, in complete radio silence, relying entirely on the inertial navigation system and his own dead reckoning calculations to find a target that existed only as a set of coordinates on a classified chart. The desert below was a blur of brown and tan, flashing past at what seemed like impossible speed. The aircraft was pitching and rolling in the turbulence that low-level flight always generates. The avionics system was displaying an intermittent fault that might or might not affect the bombing solution. And in the cockpit behind him, the pilot was maintaining course and altitude with the precise, mechanical focus that B-58 flying required. He calculated the release point, waited for the automated release signal, felt the aircraft lurch slightly as the pod released, watched the instruments confirm the separation, and then experienced the navigator's equivalent of holding his breath as he waited for the scoring data that would tell him whether the simulated weapon had hit within the required accuracy. It had. Not just within the required accuracy, within the best accuracy his wing had ever recorded on that target. He said nothing to the pilot. The pilot said nothing to him. That was how B-58 crews communicated success, not with words, but with the shared understanding of professionals who knew what the work required and were satisfied when they did it right. That professional satisfaction, that knowledge of doing an extraordinarily demanding job to an extraordinarily high standard, is what the B-58 Hustler represented at its best. It was an aircraft that asked the absolute maximum of everyone who flew it, maintained it, or supported it. In return, it offered something that few weapons in history have offered: the genuine, verifiable, demonstrated ability to do what it was designed to do better than anything that had come before it. It flew faster than any bomber in history. It navigated more accurately than any bombing platform of its era. It demonstrated, in record after record and competition after competition, that the technology and the training were both real, that the nuclear deterrence it was designed to provide was not a theoretical construct, but a practical capability, tested, and proven. That it served for less than a decade. That it was retired before its potential was fully realized. That it was cut up and smelted while aircraft that it outperformed in every meaningful measure of bombing effectiveness continued to fly for decades longer. These are the ironies and the tragedies of military aviation procurement, where the best aircraft does not always survive and the most capable technology does not always prevail. The B-58 Hustler lost the bureaucratic battles that the B-52 won. It cost too much, demanded too much, and offered too narrow a range of capabilities for a defense establishment that was learning, painfully, that the nuclear mission was not the only mission that mattered. But in the narrow domain for which it was designed, the delivery of nuclear weapons against heavily defended targets at Mach 2, it was, and remains, one of the greatest aircraft ever built. The B-58 Hustler flew at the edge of what was possible. Its crews flew at the edge of what was humanly achievable. Together, they represented American aerospace technology and American military professionalism at a specific, extraordinary moment in history. A moment when the United States was willing to invest unlimited resources and accept unlimited risk in pursuit of the capability to deter a third world war. Whether that investment was worth it, whether the B-58 actually contributed to the peace that the Cold War ultimately produced without a nuclear exchange, is a question that historians and strategists continue to debate. But the aircraft itself and the men who flew it deserve to be remembered for what they were: the fastest, most demanding, most technologically audacious strategic bomber the United States Air Force ever operated. The Mach 2 machine with the crazy crew capsule design. The beautiful, brilliant, dangerous B-58 Hustler. Now here is the question I want you to think about and answer in the comments below. The B-58 was retired after less than 10 years because it was too expensive and too specialized, but it could do things no other bomber could do. Was retiring the B-58 a strategic mistake that left America less capable of deterring Soviet aggression? Or was it the right decision to concentrate resources on more versatile platforms? Tell me what you think. And if this story of one of aviation's greatest aircraft left you wanting more, hit that subscribe button right now, because the history of the machines that defined the Cold War is far from over.